Yes. Thank you.
Good morning, everyone. Thank you all for coming. It's a great day to finally see Matt and work come together. I'm going to ask his supervisor, Michael Poza, to briefly introduce his work and introduce him. After that, Matt will speak for about 45 minutes or so, and then we'll have a round of questions from the audience, followed by a virtual session. So with that, I'm going to hand it over to you.
So Matt first reached out to me before I actually even interviewed at UC, where he was doing his undergrad. I think that sort of says something from our very beginning of our relationship about how on top of research he was. And as some of you know, here, when you join a lab that's first starting, you're really opting into a lot, right? You're setting the tone for the culture, you're developing infrastructure, you're helping recruit new students. And I've been really fortunate to have Matt here helping me and others in the lab through that process for the past 5 years. Over his time here, he's done some really beautiful deep theory diving into differential inclusions. I think some of which he may talk about today. That he's done a bunch on machine learning, has an ability to get things to work on the real robots, and this combination of everything is really rare, right? In research. The goal for those thinking about academia, right, when you start a lab, is to find excellent students who are going to push you, who are going to push the research forward. And I've been really fortunate to have Matt as the first student to join the lab, now the first student to defend. And I'm excited for him to share everything he's done here with everyone today.
Thanks so much, Michael. Today, I'm going to be discussing a few different works that we did, but there's going to be this theme connecting them, which I'm going to call stiffness. And we're going to examine and solve many challenges that it imposes in different robotics methods. So primarily, we're going to be taking an interest in robotic locomotion and manipulation by which robots move themselves and objects around in their environment. And there's a huge potential for impact in industry with these applications just in the next few years. And it both in terms of finance and impact on human safety as dull, repetitive, and often dangerous work becomes automated. And this research is going to join a huge thrust happening now in the field, focusing on the efficiency and reliability of such systems, which can be very difficult to obtain, especially when these robots need to make their way through unbefore-seen environments and interpret them so it can interact with them. In particular, we're going to be focusing on eliminating stumbling blocks that can happen in this process. So to this end, we're going to focus on a key design pattern that many of the most famous recent successes in both industry and academia share, which I'm going to call model-based control. And despite differences in the details, this paradigm usually follows the same 3 basic steps. First, you run your robot and collect some data about observations about its behavior, typically in the form of state, action, next state data points. Second, you fit a predictive or dynamic model to this data that tells you what outcomes result from different actions taken by the robot. And this model could be purely physics-based or completely learned, such as a deep neural network. And finally, you query that model to figure out which actions of the robot will lead to the outcomes that you want. And then you execute those actions on the robot. And it's this last step here that makes fitting to data or learning or system identification important, because it is critical that these models match reality closely such that their predictions match the actual outcomes on the system. And our field has encountered many difficulties in building accurate models. And these difficulties arise in very different ways with very different types of models that we use. And here I'm just going to highlight one classical and one modern approach that our field has been taking. So if you're in a lab environment, like the folks doing this robotic parkour experiment, then you may have access to a team of skilled engineers, which beyond state action pairs could meticulously and manually identify a purely physics-based model. And you could do something as simple as figuring out the masses of various objects or parts of the robots by placing them on a scale. And this process is very reliable, but these models then have to be used in real time. So often they're put into approximate physical simulation that makes many simplifications of real-world physics, such as assuming that objects are rigid. However, if you would like a robot to go out into the wild and get its own understanding automatically, such as this quadruped locomoting out in nature, then it's necessary for these models to be built automatically from data. And a modern approach coming from the artificial intelligence community to this end is to fit purely empirical models. These methods typically use very flexible architectures like deep neural networks that could have up to millions of tunable parameters. And this large dimensional parameter space gives them the flexibility to fit any calibration data. And because they can do that, they are chosen empirically to match that data as closely as possible. But despite their powerful and flexible nature, empirically, we've seen that even the best practitioners in our field have had extreme difficulty in getting them to specifically model robotic behaviors accurately. And across physical and learned models, there is something about the way that robots collide with their environment that seems to be particularly difficult to capture. And unlike applications in autonomous driving, these collisions are not accidents, but they're the very means by which robots locomote and manipulate through their environment, such as when this robot's feet hit the ground at the end of this backflip. And there's something about the fact that these things are happening very quickly or discontinuously in time that makes them very difficult. So in my research, I investigate mathematical understandings of this discontinuity or sensitivity that I call stiffness. And mathematically, we define numerical stiffness as extreme instability or sensitivity to initial conditions. And so what this means is that even on real world systems, if the system starts from a slightly different initial condition, the resulting outcome is very different. And this is something that we intuitively understand as humans. For instance, in billiards breaks, tiny subpixel differences in the initial positions of the billiards balls can result in completely different behavior after the break. And despite the fact that they are deterministic in reality, dice rolling is so sensitive that we view their outcomes intuitively as uniformly random. Numerical stiffness is both caused by and named after mechanical stiffness of the materials in these systems. And particularly high mechanical stiffness or near rigidity means that these objects are very hard to deform even a small amount. So in this thesis, we're going to focus how we construct highly accurate physics-based models in spite of this difficult property. And the essential goal that we pursued in the main breadth of this work is to combine principles both from physics-based and empirical learned modeling to create effective rigid body models, which we can construct from scratch. To pursue this goal, we are going to present three parts. First, we're going to take a deep analysis and empirical examination on why traditional deep learned models may struggle to capture contact. Then we're going to leverage the physical structure of our models to identify an alternative way of fitting to calibration data. And then finally, we are going to see how we can embed neural networks inside of physical models to learn very high dimensional unknowns, such as reconstructing object geometries from scratch. But of course, the models that we are learning in this are still approximate physics-based models, and time permitting at the end, we'll talk about an alternative direction of research that we've been doing in both quantifying and analyzing the limits coming from those approximations. So because we're going to be talking a lot about physics-based models, first we're going to have a brief background on the mathematics that underpin these models. And then there'll be a lot of equations on slides for just a few minutes, but we're going to circle back at the end and focus on one really important one that is the key message from this section. So while these robots that we're describing may be designed with high fidelity solid mechanical models, for instance, with finite element analysis, when we embed models into model-based control, we need them to be able to make predictions of dynamic behaviors through time at faster than real-time rates. So we simply do not have the computational budget to be simulating physics in this level of detail. So the most ubiquitous way in which we simplify the physics is we make a rigid body assumption. So we take objects that are nearly rigid and very hard to deform, and we assume that they do not deform at all. And a primary focus in rigid body modeling, particularly for simulation, is understanding the physical interactions through touch that these rigid bodies have. And in general, simulators approximate two physical laws. The first I'll describe is called normal complementarity. It describes the relationship between normal forces between objects and also the sign distance phi between them. This sign distance is positive if the objects are not touching, and it's negative if they occupy the same space. As no two objects can occupy the same space, in physics simulators, this distance is constrained to be non-negative. And also because objects cannot exert forces on each other from a distance, either the distance or the normal force must be exactly equal to 0. Finally, another simplification in these simulators is that we do not model adhesive or sticking effects such as materials like Velcro or adhesives. And we'll often combine and abbreviate these three constraints together in using this notation shown here on the bottom. The second set of laws describes friction, or a physical phenomenon where objects sliding against each other resist that sliding motion. So typically in simulation, we use something reminiscent of the laws of friction that you may learn in high school or undergraduate physics courses. It's called a Coulomb or dry friction model. And this model says that the friction force is no larger than some coefficient of friction mu times the normal force. And if the objects are sliding against each other, then this friction force will oppose that sliding motion as much as possible, pointing in the exact opposite direction. So when we want to embed these physical concepts into a computational environment, like a rigid body simulator, we have to be able to handle something more complex than just two objects touching each other. And namely, our robots are often articulated and have inputs such as motor torques affecting their motion. And in general, these models combine joint angles and positions of bodies in the environment into some generalization of Newton's second law, F is equal to ma, where particularly there are leverages coming from geometry that tell you how those individual contact forces affect the velocities and angular accelerations of all those articulated joints in your system. So this equation here on the top right looks something like a differential equation. But differential equations are not enough to model these systems, because if you assume that bodies are perfectly rigid and they come together with some non-zero velocity, then there is no solution or result that could happen to prevent interpenetration except a sudden instantaneous change in velocity. So that change we would call an impact, and it's the result of an instantaneous accrual of a non-zero amount of contact impulses. So these laws describe how these systems move in continuous time, but in practice, when we work in computational environments, we have to discretize the time domain in some way. And this amounts to integrating Newton's laws through time and applying these contact constraints only at the end of a finite time step of length delta t. And in doing this, we end up capturing a net contact impulse over this interval, which includes both instantaneous impacts and integrations of finite forces over time. Practically, we have now phrased simulating these systems as solving a system of equations. And the way that we implement this on computers is we solve it with numerical optimization. And this is the really key equation from this section here, is that even if you would like to take a physical simulation and simulate just one time step of a millisecond forward in time, you're going to have to solve a very complicated optimization problem. And in general, these problems are often very difficult and non-convex, a particular form called a linear complementarity problem. So with this background, now we're going to examine how we can learn the parameters of models of this type. And because we're going to be embedding deep neural networks into them, we're now going to discuss classically how the stiffness of these systems has resulted in poor learning of their dynamics. So as a reminder, we're using these learned or identified models inside a model-based control framework. And there are two key steps in here that are depending on your model learning algorithm that need to go well. One is an optimization step. It's when you fit the data, you fit the parameters of the model you have to the data that is available. And generally, when we're thinking about fitting predictive models to data, we think about the quality of this fit in terms of prediction error. So we take the initial condition in the data, we simulate with our model forward in time, and we compare it to the final condition observed in the data set. And the discrepancy between these two is an error that we would like to minimize. By some method, we'd like to find parameters theta that make this error small. But then we pretend the model that we have is identical to reality, and then we execute actions that the model thinks are good. So in essence, there's a second extrapolation step, where if we assume on the calibration data, the prediction qualities are good, if we've observed that, we're assuming that they're also going to be good at test time when we deploy the robot to do new behaviors. And in reality, this is mostly an assumption. There are rarely hard constraints that we can use to prove that these two values, L-train and L-test, are exactly aligned. So it's worth examining how neural networks perform both of these two steps. As we mentioned, they are empirically choosing parameters to fit the data as best as possible. And the way they do that is through a numerical optimization process. Essentially, you pick sort of a random set of parameters as an initialization, and then you look locally what small change in parameters would make the prediction error go down, and you take a small step in that direction. And the way we like to think of this conceptually is that the landscape of this prediction error, as you change the parameters, is convex. It's shaped something like a bowl. And so as long as you keep going downhill, you're going to end up at the very bottom with a set of parameters that have very low prediction error. But because neural networks are so flexible, they often have more parameters and data points available. There can be many different sets of parameters, many different functions that can fit this data exactly or interpolate this data. And so they have to have some internal bias by which they have a preferred method that will be a preferred function that will be selected amongst all of those possibilities. And both theory and practice suggests that our most essential deep learning techniques will try and find the function that most smoothly interpolates this data. So now that we understand how deep neural networks are learning, we can examine how those processes might interface with a very stiff dynamical system. And in particular, like I said, we're interested in test time prediction error, L-test. And I'm employing a standard technique here in machine learning called a telescoping sum, where you decompose that into a series of pluses and minuses of different values. And we're going to go through these three terms and talk about why they're important and what stiffness will do to each of them. So the first is called what I would call the oracle model error. This is if you had a perfect model of the true dynamics, but you simulated for it in time from a noisy initial condition. How bad will the prediction be because the initial condition was wrong? And if you have a very stiff model, as we defined it, that means even small changes, small amounts of noise in your initial condition can result in very different outcomes. So for stiffer systems, this first term could be larger. This second term is what I would call training suboptimality. In your gradient descent process, do you actually end up finding the parameters that actually fit the training data as well as possible? And while conceptually we would like to think this is a convex bowl-like landscape, because the model is also nearly discontinuous in the parameters, small steps or small changes in parameters can change the value of the training loss a ton. So the landscape doesn't look like a bowl, it looks more like a mountain range with many local minima and high altitude valleys and cliffs that the process could jump up or down. And so it could be likely with a very discontinuous landscape that you get stuck in a local minima somewhere and can't find that true optimum model. And thirdly, there's the discrepancy between training time and test time error. And as we explained, neural networks tend to do a smooth extrapolation, but because our dynamics are stiff, the underlying function that we're trying to model is actually discontinuous. It's not smooth at all. And so there's a fundamental disagreement with the assumptions in these methods and the reality of the real systems that we're trying to recover the behavior of. So this is a conceptual explanation about why stiffness might lead to poor model identification, but it's also important to understand the magnitude of these effects. And to do so, we've turned towards empirical analysis. So the essential approach we took was to take one system to change the underlying material stiffness in a rigid body plus compliant contact simulator and quantify how that change affects test set prediction error of learned neural network models. So we're going to highlight two key design decisions in this empirical analysis. The first is that we conducted our experiments in simulation rather than the real world. And while simulations are inherently approximate, this gives us complete control over any confounding variables that have changed other than the underlying stiffness in the system. And it also allows us to use the simulator to calculate that oracle model prediction error and compare it to the amounts from training sum optimality and generalization. And secondly, we chose to focus on a simple canonical system, which is a single die roll. And by choosing such a small dimensional system, we're able to conduct brute force optimization of all of the hyperparameters that are settings in our learning models to make sure that we're not being unfair to these methods by just accidentally picking a poor set of settings. And despite the low dimensionality of this example, as even a single die rolling is very hard to predict and exhibits many very sensitive behaviors, impacts, rolling, stiction, etc. So we plotted our results here on the right, and we show that they show that increasing stiffness and holding everything else constant results in a significant increases to test time prediction error. And particularly concerning is that the stiffness of these models, even with 100 times the calibration data to work with, still has worse prediction error than either of the software 2 stiffness settings that we examined. And overall, we find that each of the terms in our decomposition of the test time prediction error is significant, and those differences are statistically significant across a variety of data set sizes. And it's particularly important to note that the training suboptimality and generalization error can be as large or larger than the oracle model error. So it's not simply the fact that the data is noisy, there is something significant going on in our training process that isn't as good as it could be. One of the most concerning things that we note here in terms of the generalization error, the extrapolation shown on the right, is that even over a large increase in calibration data, we do not see a significant decreasing trend in that error. So what we've done so far is we've analyzed why deep neural networks might be hampered by stiff dynamics. And now we're going to move towards developing solutions where we can combine physical and learned principles into an effective model identification procedure. And when we do so, we're going to take a paradigm that I'm going to call white box deep learning that combines the physical interpretability of physics-based models and simulation with the spirit of empirical identification and learning complex quantities from scratch from the computational toolchain of deep learning. We're going to be doing this in two parts. One way is we're going to be learning a deep neural representation for reconstructing object geometries from scratch. And we're also going to develop our own novel training optimization procedure by which we minimize a loss other than prediction error. And there are many works in the community that, in the robotics community, that have inspired this, as well as the computer graphics and computer vision communities. Namely, in terms of defining our new loss, we're going to take an inspiration from the constraint violation structure that has been pursued both in low dimensional system identification and planning and control, both inside the DARE lab here at Penn and also at other universities. And in terms of representing geometries with neural networks, we're also going to be borrowing some perspective from computer vision and graphics, in which neural networks were designed to render arbitrary geometries rather than physically simulate them. And there's also a lot of other works than ours that are combining physical principles with neural networks and empirical modeling. And I just want to highlight a couple of them. Two of the most significant ones, I think, are what I would call neural physics. So these are methods that learn new laws of motion that improve on our approximate physical laws. given known system parameters. And there are also residual physics that take a well-calibrated physical simulator and then augment them with additional neural networks to model and reduce the error between those simulators and reality. Both of these sets of methods take a well-calibrated physics simulation as an input. And in general, it's difficult to get those from scratch. And what our method is doing is providing a way to provide physical models like that to these methods. So these are something that can be used in conjunction rather than competing methods. Okay, so first we're going to talk about how we are optimizing our physical models in a different way versus minimizing prediction error. But because prediction error is such a statistically well-motivated and ubiquitous metric in our community, we're going to take some time to examine why it is important, why it can be effective, and understand why for our systems it might be advantageous to use something else. So if you have some sort of model, for instance, this one shown as a green curve here, and you would like to capture how well it fits a data point, shown as a green dot here, and if you assume that this data point is noisy and the noise is most likely to be small, then a natural way of capturing this data and model match is the distance between them geometrically. And specifically, the distance between this data point and the closest point on the graph of the model. And this is a classical statistical perspective that's been studied for at least 150 years. It's sometimes referred to as errors in variables modeling. And one of the reasons it has been had such longevity is it has a firm statistical backing. It's equivalent to a maximum likelihood estimate of the noise in the data, assuming that that the noise component is Gaussian white noise with zero mean. But it's worth noting that even just evaluating this metric, as stated, is solving an optimization problem. It has to find the closest point in the graph of this model. And that could be very difficult, especially if your model is nonlinear, then this could become a non-convex optimization problem. So something else you could do is, instead of getting the closest point on the graph, just find the vertical distance to the graph. So this is equivalent to assuming that your initial condition is not noisy. And this is precisely what prediction error does. And it is related concretely to graph distance in that it is larger than graph distance. Because you're not picking the best point, you're picking a particular one. And because of this relationship and the training process is minimizing prediction error, if you achieve low prediction error, you also achieve low graph distance. And it's worth noting that, at least as stated here, you don't have to solve an optimization problem to compute prediction error. For instance, if F is a neural network, this is matrix multiplications and additions. So this is very, very fast computationally. But it's worth noting that we have a very particular antagonistic form of model. And this is this final equation from our background, which is that embedded inside of forward prediction for physics-based models is a very difficult optimization problem. So maybe prediction error is still tractable, but it's certainly not as tractable anymore. It's no longer just a few matrix multiplications and additions. Just like graph distance calculations, you are solving an optimization problem. So without looking at the structure, it's not clear whether prediction error is harder or easier than graph distance. And secondly, these models are stiff. So the graphs change very suddenly in the initial conditions. They have these near vertical sections, like the one near the x prime axis here. And if you consider a noisy data point that's very close to the graph of this model, then there could be a very large discrepancy between prediction error and graph distance. And so while it is still larger than graph distance, this discrepancy can be very large. And we find that it's particularly areas of state space and parameter space where these discrepancies occur that cause that stiffness and difficulty in optimization for prediction error for these types of models. But that doesn't mean they're not statistically well motivated. We would like these quantities, particularly graph distance, to be low. It's just we don't have an easy to optimize and easy to compute proxy to guarantee that it is low. So what we've done is we're going to propose an alternative metric, different from graph distance, different from prediction error, that is going to be inspired from some various works in system ID, planning, and control in the robotics literature. All these works have a common theme of constraint violation. So embedded in our simulation is minimizing some function h. We're getting it to its absolute minimum, corresponds to exactly meeting the physical constraints of friction and complementarity. So what we would like to do is we would like to do a trade-off between these concepts and prediction error.
Specifically, you're minimizing the impulsive forces that contribute to the violation of the constraints optimization.
I think yes, you are finding forces that are in some sense physically plausible and also match the motion that you see. You could think of this as like if your model thought. Go ahead. Yes.
So why is this right way to
I think there's a few different ways, and I'm going to hold you for just 2 slides. We're going to have a nice graph that like shows the different behaviors of these losses, and I think there are 2 very important reasons. And we have actually not even done enough work to disambiguate which is the more important, but we'll get there in just a minute or 2. Okay, so we would like this loss to both produce low prediction error if these forces occurred. And those same forces must also be physically plausible. They must at least approximately comply with the physics constraints, such as complementarity and laws of friction inside of the model. And we've combined those into our novel loss that we'll call a violation loss that trades off these 2 terms by optimizing over a set of possible contact impulses. So we rigorously theoretically analyzed this loss and found that it had a number of favorable properties. First, just like prediction error and just like graph distance, this loss is non-negative and it reaches its minimum value of 0 exactly when data points exactly fit your model. So in some sense, optimizing this loss is well correlated with both graph distance and prediction error. Secondly, just like prediction error, it is also an upper bound on graph distance, up to a constant that in many cases in robotics is reasonably close to 1. And finally, because of the different structure that we've used in this loss, we can actually pose it as a convex program that is much easier to solve than the NP-hard non-convex programs often embedded in prediction error. So that's one reason, is that it's easier computationally to solve this loss than prediction error. But there's also a practical optimizability perspective that is important as well. So remember, we are trading off whether forces are physically plausible and if they explain the motion observed. So if 2 objects come close together based off of the data points in your model, but they don't touch, but it appears that they accelerated apart, maybe you would infer that, oh, actually those objects were a little bit larger and then they actually touched and that acceleration came from them touching. And this loss is going to actively trade off those 2 concepts. And so what that results is if you compare to prediction error on this simple 1D example. So here we're plotting the optimization landscape of these various losses: graph distance, prediction error, violation loss. So this is the function that we are doing gradient descent over. So we're considering a 1D example, a point mass hitting flat ground. We have only one parameter to identify. It's the height of the ground. With prediction error, if the height of the ground is underestimated, it's lower than it actually is, then in your data, it appears like an impact happened, but there was no contact. But prediction error would not predict that there is contact. So changing the ground height a little bit isn't going to fix anything. There's a flat region of prediction loss shown in red on the left side, where changing your parameter doesn't help. There are no gradients to descent. Conversely, if the ground is assumed to be too high, then the model thinks it's in penetration, and there might be a large reactionary force to remove that penetration over your time step, resulting in a very stiff landscape that blows up to very high values very suddenly. And even a small gradient step along those gradients may put you over into the other regime where there are no gradients to learn further from. By contrast, because we are trading off violations of these properties in a soft manner, we see that as you get closer to contact, the loss gradually decreases as it sees that an impact becomes more and more physically plausible. It violates the complementarity constraint less. So you have non-zero gradients on the left side where you had zero gradients before. Furthermore, on the right side, because we're able to penalize penetration in a reduced manner, the gradients on the right are of a comparable magnitude to those on the left. And so optimizing R loss in the green landscape here is often much easier to do than optimizing prediction error, even on this 1D example. Does that answer your question?
Sort of. I mean, there's a pragmatic reason for choosing this.
Yeah.
But the question I asked is not unrelated to the discussion we had during your proposal, which is implicitly that when you adopt this approach, you are favoring inelastic violations of constraints as opposed to something with large, rebounds.
Yeah.
So when you have elastic impacts, you have bigger impulse force, and you're somehow biasing yourself against things that don't stop this.
Yeah.
And I just wonder, and then of course, and again, I very much like what you said about stiffness and how studies that you did hard, soft, and different. And again, the results that you're getting might be colored by the fundamental assumption you're using that I prefer. Inelastic impacts to that. So.
I mean, that's certainly true, and we're gonna see on real data that has a low amount of elasticity. We identified like coefficient of restitution like 0.1. It can have a significant effect to take those assumptions away. I don't think it's fundamental to this approach to be assuming inelasticity. We did have a master's student who worked on an elastic version of this that had similar optimization characteristics. It's just not something that we've prioritized over the last couple of years. But yeah, it is definitely like a limitation of these models that they are making simplifying like physical assumptions. And I think inelasticity is one of the most simplifying ones. That's particularly in manipulation.
It's 20 years of work.
That.
So,
I
get that. But.
Yeah. Okay. So going beyond a 1D example to something more complex in 3D, we're going to return to this canonical system of dice rolling. And particularly, we're going to practically and directly compare the ability of hour loss and prediction error and their ability to optimize parameters to fit data with gradient descent. And we're going to do this in simulations such that we have access to ground truth physical, geometric, and frictional parameters. Specifically, what we're going to do is collect noiseless simulated data such that there exists a model that produces exactly zero error. We are then going to learn the geometry and the frictional behaviors of the die with 25 numbers representing the position of the corners of the die, as well as the coefficient of friction between the die and the ground. We're going to initialize them to be wrong, something like 30% relative parameter error, and see if by gradient descent we can recover those true ground truth parameters. And overall, we found over multiple trials that prediction error does, as we expect, get stuck in local minima and not recover the true model. Whereas over many trials, every single instance of optimizing with our novel violation loss is able to recover the ground truth parameters to numerical precision. And visualizing how this process occurs, here we've plotted how these losses decrease over time as you take steps down their gradients. And we find that very consistently over just a few passes over our data set, that we are able to reach a global minimum very close to zero with our performance metric. Whereas various trials of minimizing prediction error can get stuck at values that are much larger than others. And as a result, ironically, the long-term prediction error of models optimized with hour loss is much better than those with prediction error directly optimized. And we overlay the data in red with the model predictions here in blue of the simulated die tossings. We're also showing the learned geometry in blue as well. And we find that for our models, they overlap so much that it's very hard to distinguish differences in their motion, while there are very clear differences in the amount of rolling and sliding in ones trained with prediction error. So this is how we would like to optimize physics-based models. And we believe that we've achieved some sort of numerical superiority in our ability to optimize them with gradient descent. And now we're going to transition to talking about new types of physical models that we are going to be learning by optimizing this loss. And specifically, we're looking to transition from the classical regime of fitting a couple scalar values like masses and coefficients of friction to reconstructing entire high-dimensional unknowns from scratch, such as object geometries. And particularly for manipulation, where robots need to interact with before unseen objects, it is very valuable to identify the geometry of those objects such that your robot can know where and how to grasp them to accomplish tasks. And this is very difficult because if you would like to reconstruct an object geometry from scratch and you have no prior information about its shape, you're effectively doing an infinite dimensional identification process. You can think of this intuitively as when we have physics simulations, we often capture the geometry of our robots with geometric meshes that could have thousands or millions of vertex points to describe complex geometries. And this very high dimensional optimization setting is not what classical identification methods were developed with in mind. So what we're going to do is we're going to describe a novel way in which you can represent arbitrary geometries and approximate them by embedding deep neural networks inside of physics simulators. We are going to show that you can approximate any shape using this method. And we're also going to show that rather than fitting a discontinuous function with neural networks, this process effectively uses their ability to do smooth interpolation for the benefit of high quality models. And the way that I would like you to intuitively think of the way that we're doing this is this example that we like to return to. It's a stroboscopic capture of a ball moving through space. Intuitively as humans, we look at the parabolic shape that this ball trajectory has and infer that it's mostly falling under the forces of gravity with a few interruptions where its velocity suddenly changes from downward to upward. And implicitly, even though I haven't drawn anything on the screen, what we do as humans is we infer locations of impacts and we smoothly interpolate between them in our mind to infer that the ground is flat. And it is exactly this intuition that we're going to directly embed into our learning process. And furthermore, we're going to do so in a way that we can re-extract those meshes to insert our learned geometries back into simulation frameworks and planning and control algorithms for robotics. So specifically to figure out how we parameterize these geometries, we're going to look at how geometries enter into simulation. And specifically, as we discussed earlier, they are used to describe signed distances between shapes that govern the contact forces between them. And this is fundamentally a function that combines two different geometries and calculates the difference between the shapes defined by those geometries. In general, this is a very difficult computational problem, but if you know that both of the two shapes that might be touching each other are convex or they only curve outwards, then there are many classical and modern algorithms that under this assumption can calculate this distance very efficiently, both classical methods like GJK, an expanding polytope algorithm, and modern convex optimization-based ones. And a typical way that simulators capture non-convex geometries is to decompose them into convex parts. And so what we do in contact nets is the reverse of this process. We are going to assume that shapes have convex parts, and we are going to build them up by learning each of those convex parts. We do this in a few-step process. First, we're going to recognize that convex shapes can be well approximated by supporting hyperplanes. So any convex shape can be reconstructed by taking hyperplanes at various angles, pressing them up against the shape, and noting by constraint that the shape only lies on one side of that plane. The position of those planes for a given normal direction of the plane is defined by something called a support function of the shape. And this support function, given a direction, returns to you exactly how far away the hyperplane in that direction is from the body's origin. And so what we do in contact nets is we're going to be learning these support functions directly as neural networks. And it's well known that if the neural network or the function you're learning is both convex and positively homogeneous, then it is a valid support function for some shape. And specifically what we're going to be doing with this, we've done this with this concept, is we've defined a new novel neural network architecture that is guaranteed to be convex in its input and positively homogeneous, extending some earlier work on convex neural networks. We have proven that these neural networks are flexible enough to approximate any convex geometry. And then also we've developed simple algorithms by sampling from which you can generate mesh approximations of those shapes by sampling the value of this function as well as its gradient. And those meshes can then be exported to simulation. So here's an overview of the learning process that we would use with contact nets. Much like all the other learning processes described in this talk, you start from state, action, next state data points. You can collect those, for instance, from motion capture. And then we instantiate a physical rigid body model with articulation. And we set all of the geometries or just particular geometries of interest to be learnable inside of this system, parameterizes these neural networks. We then optimize those physical models to fit data with our violation loss, which in this particular case can be efficiently solved for a single data point on the order of 100 microseconds. And there are well-known mathematical ways by which we can differentiate those to do gradient descent to improve those shape parameters. And then finally, when we like to use these models, we can turn them into common robotics description formats, such as URDF, and then insert them into any of our favorite simulation planning and control frameworks that process those types of files. So we evaluated this method on real world data. We actually constructed a physical analog to our die rolling system, which we track with motion capture using fiducial markers. And as we're working with a real world system, and there are going to be some approximations inherently in our physics-based models, rather than checking ground truth parameter error as before, we're going to evaluate the long-term prediction error of these learned models as our metric of interest, as if they are high quality. And we're going to be comparing our method contact nets, which combines these deep learned geometries and our violation loss, to a couple ablations or simplifications of this process to compare the importance of various components that we are contributing. The first baseline we'll compare to is what's called deep differentiable physics. What this is doing is it's learning the same type of rigid body model, but it's optimizing prediction error instead of our violation loss. And the second, which we'll call end-to-end, is the sort of baseline, learn the entire dynamics as a neural network type of application that we explored in the first section of this talk. So overall, we found that over a variety of data set sizes that our method is able to achieve lower long-term prediction error than both of these baselines. And we've computed some visualizations here of these various types of models so we can examine what has gone on in them. So here on the left, we show this baseline end-to-end method that doesn't have any physical structure. And we're showing the true motion, we're showing the model's motion with the true geometry overlaid in blue on the motion captured trajectory, which is shown in red. And I want to stress, even though these are simulated visualizations, this is real world data that we're seeing here. So we can see that these methods fail to capture qualitatively what happens during physical contact. Rather than having rigid impact with the ground, these objects just sort of drift and slide several centimeters into the ground, almost as if they were moving through quicksand. By contrast, the methods learned with deep differentiable physics have this physical structure, so they have an underlying learned geometry that we render in blue. But because prediction error is very difficult to optimize, we find that they consistently fail to recover ground truth geometry. And specifically, they have a tendency to underestimate the volume of these shapes. And in particular, they end up looking quite round as an inner approximation of the cube. And as a result, they predict motion that has much more rolling rather than sliding and coming to a rest. And then finally, our method contact nets, as can be seen in the blue geometry, is very closely reconstructing the geometry of the cube with a maximum discrepancy of no more than a few millimeters. And as a result, it has both quantitatively and qualitatively the highest match in terms of prediction and model predictions versus real data. But we do want to note again that there are physical simplifications made in this model, one discussed earlier being inelasticity of these impacts. And so we see that there's considerably more bouncing in the real world data than in the model. And future work is going to have to expand the physics of the types of these learned models to reduce that error. So there's a lot of work happening in the lab surrounding these contributions. I'm going to highlight two thrusts. One is work being led by Bianchini on applying contact nets in much more complicated scenarios. And specifically, she's interested in learning both inertial properties, geometric properties, as well as complex unmodeled physical effects from more complicated objects, such as ones with articulation. And in particular, it's important to have these learned residual components as well, because it's very difficult to model the frictional behaviors internal to the joints of articulated bodies. Another thrust is examining how we can transition optimization with our violation-based loss into control and reinforcement learning frameworks. So work in the lab being led by Wingxin Jin focuses on how you can learn a simplified local version of these physical models called a linear complementarity system. And how you can input that into a model process controller to conduct effective manipulation of novel objects learned from very little data. And you can see a simulated example of his method here, reorienting and moving this cube with a three-fingered gripper in simulation. And then outside of the lab, there's a number of other things happening in the robotics community that we think could be synergistic with some of the algorithms we developed here. Namely, like access to cameras, and particularly depth cameras, which can give you point cloud estimates of the world, is really strong sets of information for recovering object geometries. They do have their limitations, particularly when it comes to occluded vision, and we think this is a good opportunity to do some form of sensor fusion or combine these methods with the ones that we've presented here. And this could be on the raw data or learn simplified representations such as key point tracking that have been explored in the community as well. And finally, to ultimately increase the accuracy of the physical models that we would learn, it would be important to extend these methods to be able to capture more complex physics, such as models that can capture the physics of deformable objects, which is a very active area of research in robotics these days. So in summary, context nets is leveraging our novel loss, along with embedding deep neural networks inside of physics simulators to reconstruct complex quantities from scratch on real world data. But because of these physical simplifications, another area of research that we've considered over the last few years is figuring out if your computational constraints require you to use a simplified physical model, how can you capture and quantify your lack of ability to make accurate predictions based off of those simplifications? And particularly, it has been noted for a long time in both the mechanics and robotics community that not only are collisions particularly difficult to model, but simultaneous and nearly simultaneous collisions are especially difficult. And in particular, in examples like this billiards break here, the outcomes of these multiple impacts is highly dependent on the time ordering in which the various objects exert forces on each other. And it's also well known that this time ordering isn't something that happens at random. It's something that happens from the complex physics of deformation that fundamentally rigid body models do not completely capture. So without the ability to completely capture these effects, there's been a number of different proposals about how you model impacts in rigid body models that differ greatly, but all share some strong physical motivation. A first group of models that I'll highlight is called algebraic models, in which you relate the pre-impact velocity v minus, the post-impact velocity v plus, and the contact impulse that created that transition by solving a set of algebraic equations. These models might conduct simultaneous collisions by doing all of them at once in one big set of equations, or it might select some sequence of individual pairs of bodies to calculate individual impacts for. But unfortunately, because these methods don't capture in detail the process that happens in the middle of an impact, which in reality does occur over a short non-zero period of time, they disagree significantly with reality. And while they're all physically well motivated, they often use differing principles which differ in predictions from each other. And furthermore, in sequential methods, some methods may become stuck in an infinite loop of collisions, particularly when there are jamming between objects. A higher fidelity approach would be to instead say that we should take some sort of rigid body approximation, maybe with some notion of compliant contact, that can map the compliance or stiffness of materials to resulting outcomes. And these models are generally less tractable computationally, but they add this fidelity, this accuracy, at the expense of having to know more about your system. Specifically, it is known that the outcome of these models and real-world systems is highly dependent on the ratios of the stiffnesses of the various materials in your system. And in many applications in robotics, particularly when you're manipulating before unseen objects, it is not always tractable to recover these stiffness values online as the robot is behaving. So if we don't have enough information or computation to do a detailed simulation, an alternative approach would be to instead say that we know from some basic physical constraints that it's not that something arbitrary could happen. It's some set of possibilities. And that set is mostly dependent on the order in which these impacts are processed. So what if we could build a model that could capture the set of results that happen from arbitrary impact ordering? So we do make one significant limiting assumption in this analysis. We are again committing to inelastic impacts. We do think there's an extension to elastic impacts not yet explored. But we start from a very classical model of a single impact developed by Ralph in 1891. This is for a single inelastic impact with Coulomb friction. What we've done is we've developed a new formalism that extends this model to consider multiple simultaneous impacts. And the mathematical formalism we use is called a differential inclusion. This is something like a differential equation, except it says that the derivative of your system state must lie in some set. And for us, this set, elements of this set correspond to different relative rates of impacts resolving during the impact. We then compute a numerical approximation to this evolution during an impact, inspired by and leveraging much of the structure from linear complementarity-based simulations, by which we can use statistical sampling to approximate the full set of outcomes that could happen under any ordering in this model. And then we rigorously analyze these models to show that they're very well behaved. Namely, that these models will always predict at least one impact outcome. They will always resolve the impact in a finite amount of time or steps, so they cannot become stuck in infinite loops like other sequential methods. And they're always physically reasonable in that they dissipate kinetic energy. And so we've applied this method to some key examples in the literature of uncertainty in the outcome impacts. And this can happen in much more realistic scenarios than a billiards break for robotics. For instance, this example from David Remy in 2017 examined uncertainty in the outcome of even just a single footstep in a real world robot called Ramon. And additionally, some older work by my advisor considered using models like this, but without the mathematical backing for calculating how you could compute and verify that control policies will be stable regardless of the ordering of the impacts that occur. This was applied both to a 2D glider that's making a Pershing maneuver, as well as a 2D locomoting robot that controls its torso. And we really think the most important future direction of research here is to integrate some notion of elasticity or bounciness in impacts into this type of modeling. So with that, the technical portion of this talk is concluded, and there were many people that contributed to all this work over the years. And I'd first like to thank the people that are here at Penn who have done this work with me and who've been influential to me. And particularly, I would like to thank my advisor first and foremost, He's been an incredible professional and technical mentor over these many years. And I'm lucky to have an advisor that even students who are not in his lab would want to go to when they're looking for professional or technical advice. And I have had the distinct privilege of being his first student and to have gotten many hours of his time, especially in my early formative years in this program, that have really influenced not only how I think about robotics, but also about how I think about research and science in general. Something that was like very important for me about a third of the way through my process here was feeling like I wasn't very connected to the pure mechanical background that I had anymore. And Nick Motney showed up at a really critical time where I was trying to figure out if I had skills I could apply to a different area of research and machine learning. And it's through taking his class and having many conversations with him that I was able to figure out how I can apply my theoretical background to practical methods in machine learning. And I'm really happy that taking his class transitioned into a publication authored with him that I'm very proud of. And also, I'm really grateful to Wenxin Jin, who is a postdoc in the lab, who will be an assistant professor very soon, for really taking some of the ideas that were present in this talk and taking them to new levels, especially in his work in online control and reinforcement learning. It is a hope, but not a given in your PhD that you get to have earnest and exciting and close collaborations with other students. And I'm so lucky to have had not one, but 4 students who I've worked with a lot and have learned so much from in my time here in PhD. Bivit and Alp are members of the lab. And I also had the distinct privilege of working with Sam and Mihir when they were quite early on in their robotics careers. And it's really exciting to see all the great things they've done since graduating from Penn. And I'd finally like to thank the DARE Lab, which, while we might have not all had the opportunity to collaborate with together, there have been so many helpful discussions, so much technical influence, and such great camaraderie provided from everyone in our lab, which makes this very difficult process of getting PhD much easier. And long before I came here, my engineering journey has had many influential people in it. In particular, I would really like to thank my undergrad advisor, Seth. He lectured my first class in robotics. He introduced me to Michael, and he really showed me that research is something that I could be excited about and I could find fulfilling. On a more day-to-day basis, I was lucky to work with this postdoc, Ali Reza, who really helped direct me towards learning the technical skills that I needed to succeed in my PhD. And on a daily basis, I have used what I've learned in the real analysis course that he so thoroughly harassed me to take. Before working with Seth, I was a computer science student, feeling very apathetic about my interest in software engineering. But I found a passion in mechanics, control theory, and robotics, and academic research through many dear and influential friends in an undergraduate rocket club where I spent a lot of my time. And long before any of that happened, I was very privileged to grow up in a house full of scientists and engineers. I have many fond memories from my sister teaching me JavaScript when I was 13, to doing a science fair project with my dad using chemistry equipment that he borrowed from his job, to my mom's relentless fight to find every extracurricular and academic educational opportunity to prepare me as best as possible. And I really never would have even discovered this calling without them. And finally, I'm incredibly grateful to the many, many close friends that I've discovered here in Philadelphia, mainly through the community here at Penn, particularly my partner, Laura, and my dear friends that have never had a technical discussion with me, but have had such great commiserations about what it is to be a PhD student and an academic. And I will be eternally grateful for that. And so with that, I'm going to turn it over to a question and answer period. Thank you.
So you started to talk, obviously, the motivation for robotics.
Mm-hmm.
I think there's still some gap in my mind.
Mm-hmm.
At the end of your first career.
Mm-hmm. Mm-hmm.
That's like the I guess the gap I'm talking about is the role of like online state estimation, actual like control on the long horizon, like open with chaotic system. I guess one takeaway I got is like I never ask a robot to like get a perfect visual.
Yeah,
but
yeah.
I am curious what your thoughts are on like, what are promising directions to then like the insights you've gotten or like the frameworks you've developed.
Right.
Like I guess the role more like robotic scenarios where you have access to data. So, like actually or like other science.
Right.
I think it's sort of like in the slide, but,
yeah. I think there's so many different ways you could think about using the models learned here and like the lessons that we could learn from them. One is that, yes, it is intuitive to us that we wouldn't have a robot do a dice roll and expect an outcome, but that is coming from our intuition. And if we want robots to act autonomously, they need a quantitative way of reasoning about what actions are actually chaotic and what ones just have sudden changes in motion. Because even motion that isn't chaotic can have these near discontinuities and have these numerical difficulties in the model identification process and in control. Every walking robot is going to make footsteps at the end of the day, for one. And so I think models like this can provide a perspective on what actions are not only good, but are reliable, to give a computational framework that pairs with that intuition. I also think it's like important, of course, to have feedback between the controller inputs that we have in robotics and the data that is collected. So something that wasn't really discussed in this talk was the sort of episodic or iterative nature of something like reinforcement learning, which Wing-Chun has done a lot of work exploring. And there's a lot of work in that area that could be immediately compatible with the models that we talked about here, as well as Wing-Chun's models, where you're picking actions that not only are conducive to your task, but towards identification. And it would be interesting to think if there are physically motivated metrics. I can't think of any off the top of my head that you could use beyond methods that do not leverage the internal structure of these models. Do you think that's a fair answer to your question? Yeah. Okay, great.
Excellent work. I'm curious if you look into leveraging analytical contact models like first contact models.
Right.
Lack of plasticity.
Right. So there are some simplifications and discretizations of those types of models that do exist in rigid body simulation as approximations. One I'm thinking of is called hydroelastic contact. It's in a popular simulator called Drake, where it's actually looking at the volumetric overlap of supposedly rigid bodies and then sort of backing out an approximate stress-strain relationship that is going to happen due to those overlap patches. And a lot of those methods share the same optimization-based structure, say that same stiff behavior. And I think in principle, with the right development and derivations, you could take this process of a violation-based loss and take compliant but very stiff physical models to do the same sort of effective learning. But it's not something that we've explored in detail yet. Go.
Very good about that. So I just had a question about in the last part of the work when you were talking about the structure of your differential inclusion. How did you decide the set your I guess your appropriate set for solutions and have an effect on the efficiency or how well your model works?
So what this set is it takes so from this notion of inelasticity, it considers active contacts as ones where applying a normal force would dissipate kinetic energy. So basically that means that there's still incoming velocity. So pushing apart just from force times velocity is power law would reduce kinetic energy. And that's actually very fundamental to how we're getting this net dissipation over the impact process. The flexibility in the set there is that for every contact that is allowed to be active, it could be accruing contact impulse at any rate, any relative rate compared to the other ones. And you can directly map that back to thinking about deformations in different stiffnesses, whereas various points in the impact process might cause more or less finite forces in the real world, but very sudden to be accruing. And there isn't necessarily a direct analog. It's not like we're taking one of these models that depend on stiffness and just say stiffness is anything. So there is a little bit of a looseness to the inspiration there. But we do find that like the results of this model are pretty physically plausible. And for many scenarios where we do intuitively know that only one outcome would happen, it usually produces that one outcome. So an example I would use is if you're going to drop a narrow object, if you drop it flat on its face, it's probably just going to rest there. If you drop it on the narrow end, it may rock off to one side or another. And we see that reflected in the predictions of this model.
We go around of questions here and then we'll have to.
Okay, yeah. Yeah, let me open with some lowish level questions and I kind of, depending on time, kind of work my way up. I noticed when you were evaluating the violation constraints that you started in a neighborhood of the violation box, right? You started in a neighborhood of the parameters you were hoping to find. And I assume this is because you were afraid of finding local minima in the parameter space.
So I'm not sure what you mean by starting in local. Are you talking about when we were doing this one, we're starting with 10 to 30% relative parameter error?
Right. Yeah. And it looked from your results that this was not actually necessary for your model because you were basically fitting the right parameters regardless of where you started. And I was wondering if you could elucidate a little bit what do you expect to happen if you start with completely random parameters? You have no priors on where the parameters are.
Right. So yeah, we can talk about this in terms of the loss optimization landscape. So when you look at this window, it looks like there's a significant and reasonable gradient that you could descend everywhere. That is not in fact true. There will be some points off on the left side where it does become completely flat, where any amount of contact impulse would violate those physical constraints so much that you just decide to not weight them at all. And you can actually think about re-weighting the prediction error portion and the constraint violation portion to manipulate the size of those regions. Another thing we'd note is like you could rescale the constraints very highly, and this would be a very close approximation of prediction error. And we found that in some cases, if you scale it with 1 over dt, this could actually be exactly prediction error because we're using sort of like an L1 violation. Eventually, you get lasso-like snapping to 0, and it turns into a 0 norm regularization. So there is a design parameter that's kind of hidden here that we're not really discussing that you could use to do these sorts of trade-offs.
Gotcha. So let me proceed to the contact net portion of the talk. I have a question there about how you were setting up the network architectures. They have, the way you set up your network architecture is going to specify something about the capacity, which I think in your case maps to something like the number of planes you're using.
Exactly.
To approximate.
Precisely.
So did you have to tune this to the particular objects that you were using?
Right.
I'm also kind of curious to know why you restricted your studies primarily to kind of like fluids and objects.
Right.
Is this related to some capacity issues or?
So yeah, so 2 questions. The first was on, remind me, the first question was on
the architecture, the number of
architecture of the network, and then why focus on cuboid shapes. Okay. In terms of the architecture, in practice, we instantiate, so these are ReLU neural networks. The weight matrices are passed through exponentials, so they have positive entries. That gives us that positive homogeneity along with convexity. We also don't have any biases in support of the positive homogeneity, but we do have input injection to every single layer. So they are quite flexible. It gives us that universal approximation. In practice, these networks essentially just modified MLPs. We do like depth 2 and like weight 256. And at that range, like you could get really like a large number of hyperplanes in terms of expressivity of networks. ReLU neural networks have like quite a large number of linear sections, which each linear section comes out to a vertex in a polygon, even for a relatively small amount of parameters. So we find with 2 and 256 that evaluating the networks, the weight there is relatively small versus solving the physical constraints. And yet it's more flexible than we think you would ever need. You could see like just visually, it's funny that we will be using the wrong geometry to take a look at this here, that you could see it's basically with hyperplanes reconstructed like a spheroid in the middle plots here. So in practice, we just don't think this is something you really have to think too much about in terms of an individual network. Something you do have to think about is how many convex parts does your object need? Because that is something right now that we just hard code. And I'm sure there would be some method to start with many networks and some sort of regularization to like discover that you don't need to use many of them. And also, even if you used a ton of convex parts in the learning process, when you export to meshes, there is opportunity to simplify the geometry before it's input to a simulator there. So in terms of inference, planning, and control, the number of convex parts in your learning process won't have an impact there.
The results in the middle, which is what we're finding at, right?
Mm-hmm.
Face the sphere.
Mm-hmm.
These results are created by the same network architecture, but
Yes.
trained with a different law. Right?
Training with prediction error, yes. Yes.
And how many have?
So it's not using hyperplanes directly because these are neural networks dynamically. It'll choose the number of hyperplanes that fit its geometry. For rendering, I used on the order of 250 hyperplanes, and practically every single one is distinct as we would find it.
And most of them are basically they are degenerate in this case, right?
They're pretty close to degenerate. We actually do find some little nuance here is like, this is not, the real world object is not a perfect cube, right? You can't actually manufacture a perfect cube. It has some rounding on the corners so it doesn't fracture when you toss it on a table. And actually, by zooming in on these meshes in detail, we have found that it actually discovers those slight little rounding behaviors at the corner. Yeah, yeah.
I'll just ask a question when you're on the slide. So
yes,
you're experimenting, measuring the outcomes of your experiments, and there's errors in those measurements.
Mm-hmm.
And to what extent, how do those errors relate to the decisions that you make?
Mm-hmm.
In other words, I mean, I don't know what accuracy you're getting, and I'm
yeah,
you benchmark that, but I just wonder about the loss function, the ability to pick the model, and
yeah,
say, well, this is better than that.
right. So we'll just quick jump up to 40. Okay. So we'll jump up to this slide. So when we did the simulated experiments to measure stiffness's effect, this is quite a light connection. But we did actually, so we have this sort of like factor graph, April tag tracking system we use to do the motion capture, which gives us uncertainty estimates. And from those estimates, and also our, direct, manually looking through the data, we were able to get rough approximations about what level of error exists in our real world setup. And then we did mirror that in this simulation setup. And so I recognize it's a very light connection, but we did find here that the noise in the data was a significant part of prediction error, but it wasn't all consuming. Even with the simplifications of physics, we did find that both generalization and training suboptimality were very significant in increasing the error of learned models. In terms of maybe a slightly more detailed look at the quantitative results on the real world data, what we were finding is that it's very difficult to intuitively put up one number that we can understand as humans. This is the best we could come up with. So this is what you're seeing is averaged over trajectories, averaged over trials, averaged over time steps in the trajectory, the angular difference between the prediction and reality, and also the linear distance. And the linear distance is normalized by a characteristic length, which is roughly the side of the cube. So I don't know that I could say something nicer than something like 1.0 looks about as close as you could hope to get with a physics simulator. It's not going to capture all those little bouncing effects. Sometimes when it lands at 45 degrees, it'll tip one way, the real world cube tips the other way. But you look at it and you say very clearly, this is a cube. It's physically rolling and having stiction, friction, and coming to rest on flat ground. And maybe also a little more detailed look at this. Here I plot both the training and test errors. Because they're physically structured, we always find, even if the geometries are wrong, that there's good agreement between training and test error. Because we have this very physically structured model that behaves in a consistent way. But we actually do find that for the neural network models that they do perform better than contact nets on the training data set. They're better able from their flexibility to fit training data, especially in low data regimes, or really actually only in low data regimes. But it's that really high generalization error, that discrepancy between train and test that contributes to them being worse overall.
I think you were going to maybe address the second part of my question, but
yes,
I think the question was just to remind you, have you actually, I mean, or let me reframe the question. Have you or others who followed up on this work tried to work with more complex geometries and shown that these methods continue to work well? Perhaps like something that is partly it retains the flavor of having corners and things that are hard to model well, but also maybe it has some.
Right. So there's two things I want to decouple here. One is, why do we use cuboid shapes? And this is a very nuts and bolts answer, which is that we were tracking them with April tags, and you need to put April tags on a flat surface. Yeah. We do think that there are a number of different ways to transition away from that. We have some students working on using modern model-free object tracking with depth cameras to capture that data, and also fusing the point cloud data with the learned geometries. But there aren't any really compelling results in that area yet. I'll also say that Bibit in her work did sort of work with random polytopes in simulation. And she was doing a harder learning problem. She's also learning these inertial effects as well. And the performance wasn't as high, but we do still see that the training process is reliable. We are at least partially recovering the behavior. And I think there is a lot of work to be done in transitioning to more complex systems. And also, for what it's worth, I think in some cases, just the right thing to do is just give up on the entire physical model, just do a local model like Wing-Chun does. And that may be good enough for your application.
So just on the same slide that you, this is a very low level question, but on the slide where you were showing the decomposition of eventual error into oracle error.
Are you the quantitative slide or the conceptual slide?
The conceptual slide.
Okay.
I was wondering, because the way that you explained this, the oracle error is only error from observing the state incorrectly, but it could also be, but is there anything in your analysis that prevents this from also incorporating errors in the actuation?
Right. And I think it's a philosophical question, right? There's some question of is it possible to have error in actuation? Or do you conceptually consider your input to be the actuator command or the actuator output? I think there's been a lot of really impressive work in modeling the internal dynamics of actuators. And something that's nice about that is you could do that on a test bench, the individual actuator, and then just deploy and copy that model across many actuator instances. And I've seen this used to really great effect from some folks at ETH Zurich for quadrupedal locomotion, specifically with Animal. And I think in working more with integrating, say, contact nets with learning about geometries through interaction in a complicated robot, I think it's a reasonable philosophy to say we can start with a really well-calibrated model of the robot itself. And it can include things like residually learned physics like Bibit works with. And then because we have this physical modular structure, we can just make the objects that it's interacting with have learnable parameters that are fit with the aid of all these known components internal to the robot.
But I think from my understanding of the analysis, it actually really doesn't matter, right? You could very well incorporate errors in actuation. But in a very pragmatic way, errors in actuation would correspond to errors between what actually is executed and what sense, either through proprioception or through an effort command.
Right. Yeah, I would say another thing is depending on the data you have available, this could be something you decouple, right? If you're modeling the inputs, the actuator outputs, and you're sensing them through, for instance, series elastic actuators, you could have that be the input in the model and completely worry about the actuator dynamics as in a separate learning instance. Yeah.
Okay.
Just find it. Okay, you can switch to both those.
Yeah.
But Michael, do you have any questions?
I'll ask one open question. So how, having gone through all this, right? You start with this X new to X, perspective. How do you feel about getting rid of the X from the input, right? So getting rid of the state information. What's the right?
Yeah, I think there are a few different ways you could go. I think one of the reasons that this loss performs well, this violation loss that we developed, is that we haven't proved this rigorously yet, but it appears to qualitatively and quantitatively match the characteristics of graph distance error, which is performing a probabilistic inference. And we've also seen these sort of probabilistic inferences over noisy measurements, inferring states from them, do very well in many other areas in robotics, and particularly thinking about methods built on factor graphs, for instance. And as a clear upper bound on a hard to compute probabilistic quantity, I think there are many ways you could integrate them into frameworks like that. So that's maybe in a way of thinking about reconstructing, doing state estimation and learning at the same time from limited observations. Another way of thinking about it is, again, just using the physical structure. Instead of thinking about learning from states as a whole and like inferring these contact forces, you could also fuse that with contact force sensors. We often have 6-axis force torque sensors in end effectors that we could directly use to capture what forces an object experience. And then through methods like that, you might be able to completely decouple the dynamics of a manipulator from just one moving object that it's trying to manipulate and set up a much simpler training process.
Very good. Right, for attending.
Thanks everyone for coming.